So, hi everybody, and welcome to the BioExcel seminar. So this is the first webinar that we have for the new BioExcel 3. So, but we go on with the series that we had before. And so this webinar is number 68. And this time we have the title of the webinar is What is New in GROMACS 2023. The presenter of today are Berk Hess from the Institute of Technology, Stockholm, Szilárd Páll from the Center for High Performance Computing that is hosted at KTH, also in Stockholm, Andrey Alekseenko from the Royal Institute of Technology, Stockholm. I'm hosting this webinar. I'm also from the Center of High Performance Computing at KTH. And with me is Otto Andersson from the Finnish IT Center for Science. The webinar is part of the BioExcel webinar series, and this series is recorded. So I want to be aware that the webinar is recorded, and we will, after post-processing, the recorded video will be posted on YouTube channel from BioExcel. So during the webinar, you can ask questions. You can use the Q&A function at the bottom of the Zoom application. Depends which operating system you have. You can have this symbol on this other symbol. When the speaker are speaking, you can just type your question. At the end of the webinar, I will read the question, and the speaker, according to their competence, they will answer to the question. Please write the question also during the whole webinar. So something about today's presenter. So Berk Hess is professor of theoretical biophysics, and he has worked for a long time on algorithm in GROMACS simulation package. Actually for over the last 2 decades. And his research focus currently is advanced sampling methods, aggregation of molecules, studying on wetting of surface at the molecular scale. And Berk will start with the webinar, then we will follow with Szilárd. Szilárd is an HPC researcher with a background both in computer science and computational biophysics. And since 2008, he worked with GPU accelerator and key algorithm in molecular dynamic simulation. He authored the first heterogeneous CPU-GPU parallelization of GROMACS, and actually his interest current is efficient anachronism task scheduling and strong scaling in AMD on scale heterogeneous architecture. And then we will follow with Andrey Alekseenko, that is a researcher of SciLifeLab that is located also in Stockholm and is part of KTH. And he's one of the core developers of GROMACS, and he has worked a lot on SYCL, and he has improved performance and portability across different GPU architecture.
Yes, thank you, Alessandra. So I will continue with the main introduction to what happened in this new version of GROMACS, and then later on pass the word to Szilárd and Andrey. Let's see, go full screen. Yes, okay. So this webinar has the title, What's New in GROMACS 2023? So we tend to have a webinar each year when a major version of GROMACS is released. So in this case, the GROMACS 2023 release was on February 6th of this year. So we tried to release early in the year. So the main version number matches the year of release. And we just released a first patch version 2023.1 on April 21st. If we're talking about version numbers, then I can just clarify, because maybe not all of you are familiar with how our versioning number works. So we have 2 numbers. We have this scheme since quite some years now, which is also a popular scheme in general, is to have for first a major version number, which in our case is the year. and then a minor release number, which is the dot after the dot, which indicates the minor release or bug fix version. So good to know here is that minor releases only contain bug fixes and maybe documentation improvements. So a higher minor version release number is always better since it has more bugs fixed, and since no features have been added, I mean, there are no bugs added. So a higher version is always better to have in terms of the last number. Okay, so let's have a look what we did for this for this 2023 release. So actually, this is one of the first times we have no major new functionality. So there are a few small things that we added in terms of new functionality. So this version focuses a lot on performance improvements, and in particularly on GPU performance improvements, as GPUs are nowadays, well, in general, HPC, but also in workstations, are the most powerful compute units. And in particular in GROMACS are very used quite a lot, as you're probably aware of. So in terms of features that we have, so we have now switched the update or the integration to the GPU. So this can give quite a lot of performance improvement in many cases, because this means we don't need to transfer the data back to the CPU for the integration, or actually keep the data on the CPU and move it back and forth. So now we can have steps, or we already had this feature, but now it's on by default to have the data reside on the GPU, so GPU resident mode, as that's called. So that can give quite a nice performance improvement in many cases. Then a technical thing is that we decouple the pair disk construction frequency from other things. So now the NSC list option or NSC list parameter is completely independent from everything else. That makes life a bit easier, especially for us developers, but also for user. Then what I'll go into the next slide is our coupling frequencies for the thermostat and the barostat, which are now default set to 100. That also gives performance improvement. Then one major thing has been the extension of SYCL support. This will be discussed by Andrey later. And we have support for CUDA graphs. So that's a new feature from NVIDIA. A general new feature of which GROMACS can now make use. So Szilárd will discuss this later, and also support for PME using multiple GPUs. So also Szilárd will discuss that in his part. Okay, so I'll just mention the thermostat and barostat improvements. So here, the general issue is that to apply a thermostat or a barostat, we need the temperature or the kinetic energy, and for a barostat, we also need the pressure. And these are global quantities, so we need to communicate over all ranks, processes involved in simulation. This is expensive, so therefore we want to avoid doing this too often. And to reduce these costs, we have introduced quite some time ago that we don't need to apply the thermostat and the barostat every step, but we do it every n steps, and that's what the NSC couple and P couple are for. So they were often default something like 10 steps or so that would still cost significant overhead, not only in terms of communication, but also because when using a GPU, this means a lot of work needs to be done on the CPU with those steps. So now we set it to 100, which means that the overhead gets small, except for if we require at least 5 steps per coupling time tau for first order coupling, like V rescale and C rescale, and 20 steps per oscillation for those Hoover and parallel Raman. So this improves performance, and also, well, it makes also some things simpler in terms of choosing NST parameters. But also, I think it's a good point to state our recommendation nowadays, which is not really an official recommendation, but in practice is usually good, is to use, for temperature coupling, use the velocity rescaling thermostat with a coupling time of 1 picosecond is usually good. And the cell rescaling for pressure coupling with a time constant of something like 5 picoseconds. And avoid the second order coupling of Hoover and parallel Raman, which can cause issues due to oscillations. So these rescale thermostats produce the correct ensemble, unlike the Berendsen thermostat and barostat. So they're fine to use. Okay, so now I'll continue with some general information on GROMACS, not so much what you do, but maybe not all of you are aware of different aspects on the GROMACS project. So this is the highlights that we have on our GROMACS website, www.gromacs.org. So this has our reps. We had a website very long ago, but it disappeared, and now since a year we have this. This was announced at the last webinar also. So here you can learn about important major features of GROMACS and read a bit about this. And there's links to tutorials and to publications and such. So this is nice to look at, see what you can do in terms of advanced methods. Then we thought it's also useful to discuss what we can do in terms of interaction with users and also developers. So first for users, well, there's the web page, as we just discussed. There's the documentation, which is on manual.gromacs.org. Then we have a lot of tutorials which have been developed mostly in collaboration with BioExcel. So this is at tutorials.gromacs.org, where you can find those. Then, as we said last year, we have the forums. So these now are become very popular. So we have more than 100,000 views per month. So here you can ask any questions on usage and installation. You can also follow releases, release announcements there. There's a development section where you can discuss ideas on development, and there's a third-party tools and files section also for the community. The forums have become a big success now, I'd say. So we actually get fewer questions in a certain sense, which is good because people tend to find questions back much easier on the forum than before on the mailing list. So the very common questions people can find the answers to, and others don't need to answer anymore. So the forum is now more for more advanced questions and recent issues, which is quite useful, I think, both for the users, but also for the developers, that they don't need to answer the same questions all the time. So this has been working great. Then for developer communication, we have the developer forum, as said before. We also have a bi-weekly video meeting, which is announced on developer forum. So this can be joined by anyone that is interested in development or just seeing what's going on. So this is a 1-hour meeting on Wednesday afternoon, bi-weekly, where we can discuss different things. There's now a Slack channel set up for which you need to ask on the forum to get an account there. You can file a issue on GitLab. So this is also for users, not only for developers. So if you think you found a bug, then you can file an issue there with the way how to reproduce it. So that's where most of our development happens on GitLab. Here we track issues, we upload improvements to the code, and we review them and such. And then finally, I can mention here is that we're working on a workshop on learning how to code in GROMACS. So this is being planned for this September, a workshop for selected few people that where they can learn how to develop in GROMACS and how to develop a large code, also the development environment. We'll announce this later when we've set up the whole workshop. Okay, then before we go to the new GPU features, I think we need to discuss the validation. So this is a bit problematic in a certain sense. So, but yeah, things are going in the right direction. So I should say over the past decade, our standards for testing have increased a lot. So before, when I joined as PhD student, that's 2 decades ago, I mean, people would test inside the group, but then the code was also far smaller, and things would just make it in, but then also the users were much smaller, so there's less responsibility. So nowadays, since GROMACS is such a popular code, we need to make sure that new features that enter the code, that they're well tested before users use them. They expect stable features. Now, there's no guarantees, but still, of course, we should do our best to test new features in the code to avoid bugs causing wrong results or crashes. So the main issue here is that testing is very challenging due to an exponential combination of types of input systems. Then different MDP settings, you can have like different electrostatics methods or different couplings and so on. Then there's different CPU, GPU combinations and communication code paths. So you can run part of your calculation on the CPU, another part on the GPU. You can switch that around. Then you can communicate in different ways or not, and so on. So that's very many different combinations, and then there's different hardware on top of that. So, and all these things multiply. So there's a lot of different code paths that can be taken, and this makes testing challenging. So we do some testing, but we don't have an official procedure yet. We're working on that, on an official validation procedure and a validation set. So most of the new features that are going to be described soon by Szilárd and Andrey, they have received some of them quite a lot of testing. So some of them we would say are ready for use about now. But most of them we still term experimental and are hidden behind environment variables. So there's a list of environment variables here. We actually don't have a good place yet. We're also working on that to make a list of these new features and also give a rough idea of their state of testing. I think that would be very useful for the users, but that's still being worked on. So finally, when a feature has had sufficient testing, it will get turned on by default, like for instance, GPU update happened for this release. So Szilárd will mention some of the environment variables and features and their state in his part of the talk. So I'll stop sharing and Szilárd can continue from here.
Thank you for the introduction. I hope my slides are live. So in the next part, I would like to discuss an extensive set of improvements that we have made to the GPU acceleration and heterogeneous parallelization of GROMACS in 2023. And first, I would like to give an introduction to the state of our parallelization, and I would like to motivate the directions we have taken with new trends and challenges, and in the interest of new users or those users who may not be familiar with our features that we released in the prior years, I will give a bit of a recap of the key features that the new features are built on, and which are very crucial for going forward on the future architectures. And in the following, I'll discuss some features related to strong scaling and scaling across multiple GPUs, improve scheduling with CUDA graphs, and later, as Berk mentioned, Andrey will talk about SYCL and its portability and performance and production-related features. And before jumping in, I would like to highlight that this work has been a collaborative effort, and given the state of computing, the complexity of hardware, and the challenging nature with the end of Moore's law scaling and more parallelism, we are strongly collaborating with a number of partners, including vendors and academic partners and compute centers, and we'll mention those throughout the talk, these partners. So what characterizes heterogeneous hardware these days is an increase in diversity. And what I wanted to illustrate here is that unlike a couple of years ago when we first started to target GPUs and CPU plus GPU combination systems, there were only these green blocks, NVIDIA GPUs with some CPUs, perhaps one or two GPUs. But these days we have AMD GPUs, Intel GPUs increasingly. In workstations and in servers, we have a variety of topologies and interconnects and combinations of how network CPUs and GPUs are combined. And we would like to target all of these, and the scope and scale of the variety of architectures is ever increasing. And most prominently, heterogeneous architectures in HPC is a particularly challenging landscape. The architectures have been trending towards more integration, and the network coming closer to the GPUs, the CPUs and GPUs coming closer to each other, unlocking new functionalities that allow making molecular simulations and computational studies more efficient, but also these come with challenges in targeting these architectures and exploiting these new hardware features. So to give a quick recap of what the GROMACS heterogeneous parallelization is built on. As an introduction, on the top, you see the homogeneous scheme where we compute some forces in a loop, and then we repeat that, and sometimes less frequently in an outer loop we do some pair search or decomposition. Traditionally, we started off with the force offload parallelization on the left side, where the CPU does the integration and forces are computed on a GPU as an offload engine. Later, we moved on to the GPU resident parallelization, and we call this GPU resident because the state of the simulation resides on the GPU for a number of iterations, tens or even hundreds of iterations enabled by algorithmic improvements we made over the years. And this means that we focus on keeping the GPU busy and might give up some CPU utilization and might give up the CPU, using the CPU for the simulation in order to make the most of the very powerful GPUs these days. However, in this mode, we can also make use of the CPU as an aid, as a helper to compute both for performance and to support the wide variety of features that GROMACS has. And these two modes where the CPU does not contribute in the inner loop, we call GPU only, GPU resident mode on the top right. And this means that in the hot loop where most computation happens, the GPU computes alone and no CPU contributions come in, or the hybrid GPU resident mode where the CPU also contributes, for instance, with bonded forces or pool or some AWH contributions. Another very important key feature that we designed and developed in our NVIDIA co-design project was the direct GPU communication, which was introduced first in 2021 for thread MPI and later in 2022 for GPU over MPI for multi-node simulations, which makes use of internal networks like NVLink and allows avoiding staging data through the CPU. As shown in the red, data could go through the CPU to communicate between two GPUs, but we want to take the direct path shown by the black arrow. These are key features that we have recently built on, our new features. But before talking about the new features, I would like to highlight the great scalability that these features provided. This is a simulation, performance of a simulation of a large homogeneous system, an ethanol system, where we wanted to evaluate the GPU domain decomposition halo exchange alone. Therefore, it's a reaction field system. And we scaled up to 1600 GPUs or 400 nodes approximately, peak scaling around or slightly under 10,000 atoms per GPU, and with a parallel efficiency of 40 to 50% with only 40 to 50,000 atoms per GPU. So this is the key that allows you to get good performance. However, many people want to use long-range electrostatics, and therefore PME is a key component that we also needed to accelerate. However, PME has traditionally been locked onto using a single GPU or CPUs because PME requires 3D FFT computations, and small 3D FFTs that we generally use are very hard to scale, especially across GPUs. So in this co-design project, our goal was to lift the limitations of a single PME GPU, and with that, allow further scaling. And what we did here is that we worked on firstly the redesigning algorithms and taking a different approach where we reduce grid overlap instead of redistributing coordinates. And we also added a new algorithmic pipelining to be able to partially or to a great extent overlap the communication between our PP ranks and our PME ranks so that the PME can start computing as soon as any data has arrived from at least one PP rank. So for the PME decomposition, what our requirements were MPI only for now, and for scaling FFTs, we still need a fairly fast network. An overview of what has been available before and what is available now, brand new in the 2023 release. In 2022, we had very limited support, and we only had the ability to run hybrid mode with some limitations where the FFTs run on CPU, or very limited Hefty support. Hefty is a portable library, but the performance was still not there. What we really needed is a bit more work on optimizing the decomposition algorithms and the fast FFT library. And in 2023, in the 2023 release, we have much improved performance and scalability by optimizing various algorithmic aspects, but also by working closely with NVIDIA to define our needs and waiting for a fast FFT library, which materialized in the CUFFT MP library, which is an efficient distributed FFT library, and it performs really well, as you will see shortly. And last but not least, we have added early SYCL port with Hefty to GROMACS 2023 with native backends for AMD, Intel, and Andrey will mention details about this a little bit more. So some of you might have seen already these results. I'll just want to give you a glance of how the new GROMACS 2023 performs on heterogeneous hardware. CUFFT MP is the recommended library for production on NVIDIA hardware because it's currently much more efficient than Hefty. And on these curves, the top is STMV and the bottom is the BenchPep large 12 million atom system. And as you can see, the red curves are no PME decomposition, so very limited in performance because we cannot get more performance from GPUs. The blue shows when we use direct communication, but without PME decomposition. So at 2 nodes, scaling stops, but it still provides the direct communication at a factor of 2-3 improvement. However, when we add PME decomposition from 4 nodes, the performance keeps increasing, and with the smaller million atom system, we can scale up to 3264 A100 GPUs with a 3x improvement at peak, and the large BenchPep system scales. We tested it in this case only up to 64 nodes. Likely it scales to higher too. And for such large systems of multiple millions of atoms, we get a 32x improvement at peak. So that really unlocks performance for those who have such large systems. So how to use in practice? You need to enable this, as Berk mentioned, with an environment variable, since it's a feature that has not received a very extensive testing yet. What it requires, you need to enable direct GPU communication with the environment variable shown on the slides. And you should also enable the GPU resident mode, which you can do with -update GPU. It works both with combined PP, PME, or separate PME ranks, but in our experience, separate PME ranks are nearly always faster, typically with a 1-to-4 ratio of PP to PME, but this might vary, so you need to test for your case, for your systems. Typically, a single MPI rank per GPU is best. So try with that first, but with a large enough input or few GPUs, you can try 2 ranks per GPU. That might give a little bit of extra performance. One thing to consider specifically for scaling is affinities, CPU, GPU network. These machines are complex. So please look at your compute center's guides on how to set affinities and try to make sure that the PME GPU is placed close to the network interface, and try to make sure that you use both job affinities via scheduler or MPI launcher, even if you then use pin on, because this will make sure that the runtime threads, that is MPI's own threads, CUDA, CUFFT, SYCL's threads, they are all set, and they all reside close to the application threads. Next, I would like to talk about another co-design project where our goal was to explore new ways to schedule molecular dynamics, new algorithms, and new technologies to hopefully improve the efficiency of utilizing such large devices like GPUs, which these days come with 100, 128 compute units. And the available parallelism can often lead to underutilizing them, and GPU launch overheads can often starve GPUs. And that's what I wanted to illustrate below, where I show on the left side scheduling with a traditional way of using streams where the CPU does the scheduling, and the scheduling has a certain cost. And if they're on the right side, the GPU tasks are very small, then these gaps will appear between the GPU tasks, and therefore the GPU will idle, and the GPU utilization will suffer. What CUDA graphs allows is to launch multiple activities at once, so multiple computations, data transfers as a graph of tasks defined as a single entity, and this allows reducing overheads. But also, the runtime has an opportunity to further optimize execution because it can know in advance what is the structure of the computation and the dependencies between the different computations. So as you see on the right side, the same blocks as on the left, the GPU activities are now much more packed, and this will, for such type of workload, this will make the execution more efficient and will reduce idle. So how did we go about making use of CUDA graphs and this graph-based scheduling? If we take the GPU-only GPU residence step that I mentioned before, we have some CPU work, but that's all outside of the gray inner loop. So there's the CPU in this case does not have any contribution there, and we have various dependencies of tasks in the inner loop, and we need to express these as a single graph of tasks. So how do we do that? We do that by utilizing a CUDA feature called capturing. We capture this work in the inner loop shown in the green box, and then we build a graph illustrated on the left, which is an actual extracted version of the actual CUDA graph that we recorded on a single rank, single GPU execution. Now, we could record and replay for every single MD step, but this will be inefficient because instantiating the graph has a certain cost. And therefore, what we instead want to do is to update the graph after each domain decomposition, load balancing, or after things change in the outer dashed blue loop. And with this, we can then record once, and then when the next decomposition arrives in the blue region, we just do an update step. CUDA graphs can work with multiple GPUs too, and this is where we have pushed the limits of the GPU runtimes and have worked closely with our collaborators to improve both the CUDA graphs runtime as well as our algorithms to express things in a way that makes execution most efficient. We rely on our thread MPI parallelization, and therefore what we can accomplish is to capture all activities within a single node or multiple GPUs in a graph and launch each and every step on multiple GPUs as a single launch operation, both communication and computation. And this allows very efficient execution. And what I show here, it's fairly large, so the details might not be visible, but what we have here on the left is a PME GPU doing multiple operations, FFTs, and various operations. And on the right, there are two PP GPUs, and then this is a task graph expressing that work. So what kind of performance can we expect from this? Performance actually improves across the board. Here I show relative performance compared to streams, left for a single GPU with various system sizes, and right for multi-GPUs. And performance improvements are anywhere up to 10, 12, 13%, so that's good. And further gains are expected with CUDA graphs improvements. But most importantly, we have identified ways to schedule molecular dynamics much more efficiently, and we believe that this will provide us a better algorithmic approach for future architectures, and we will be taking this further to multi-node and combining CPU, GPU tasks as well. So finally, how to use CUDA graphs in practice. What you need is CUDA 11.1, so nearly all the same requirements as GROMACS itself, and it works on any supported NVIDIA GPU. slight limitations. You need pure GPU resident mode, so GPU only, no CPU forces, single node only because we rely on thread MPI for multi-GPU, and therefore single PME GPU is supported only. And how you use it, you need to make sure that you have a thread MPI build. You can check the GMX version header for that. Offload all force work. By default, not all of it may be offloaded. These depend on internal heuristics, so best specify all options as shown on the slide, and then you enable the feature with an environment variable. And next, I will give the word to Andrey. He will talk about the SYCL-related updates.
So, in general, GPU backend is a technical detail that probably not many end users benefit, but it is a big deal for us developers. And using SYCL as a vendor-neutral standard to program multiple different GPUs allows us to focus more on fixing bugs, improving performance, and delivering new features. So, that's a big shift in for GROMACS to be able to target all the new hardware Szilárd mentioned, the new AMD and Intel GPUs, while reducing the maintenance burden on the core team. And while SYCL itself is just a programming standard, we support 2 of the existing implementations of that standard, HipSYCL, also known as OpenSYCL, which we recommend for using for AMD GPUs, and Intel One API DPC++. That is our recommended backend for targeting Intel GPUs. And in 2023 release, we did a lot of work on optimizing SYCL performance. SYCL debuted in GROMACS in a very limited with a very limited feature support in 2020. But now we worked out on features and optimizing for the most recent AMD MI250 GPUs that are present in, for example, Lumi, Dardale, Frontier, and for the coming Intel Vecchio, also Intel data center GPU Max. And yeah, we support with SYCL a lot of the nice features supported with CUDA, such as multi-node scaling for PME and general GPU over MPI. However, a word of warning, SYCL itself is still in somewhat early stages, both as GPU backend in GROMACS and the specific applications we are using in general. So please pay attention that your results are correct. And if you have any questions, sure, ask them in our forums, because we did a lot of testing on our side, but in terms of real world and GROMACS users doing testing, it's much less mature than CUDA. So our documentation is not as extensive. We might not cover all the edge cases. We haven't tested as many different hardware combinations as are theoretically supported. And yeah, so please double check that things work, and if you have any issues, reach us for help. And since SYCL is rather new technology, not officially supported by AMD, if you have a local cluster with AMD GPUs, it might not have HipSYCL installed, but you can always ask your sysadmins to install HipSYCL there, so you and other users can benefit from this nice portable backend for GPU code. And this work, GROMACS SYCL, was done with lot of help from Intel and SYCL teams. In terms of feature support, GROMACS SYCL backend is now nearly feature complete with CUDA. It supports most of the nice features that Szilárd mentioned. It's GPU resident mode, it's direct GPU communication, and PME decomposition. We have a little asterisk here because we added it very late in our 2023 release cycle. So the testing and especially performance tuning for PME decomposition with SYCL is a bit limited, but it's fully feature functional backend. And compared to GROMACS 2022, we added the bonded force of load support, added direct GPU communication, and the PME decomposition. So as it stands here, you see the hardware compatibility matrix, and it's circled are the recommended configurations. So if you have NVIDIA, we are recommending you to use CUDA. But for all generations of AMD and Intel GPUs, we recommend to use SYCL, either one API for Intel or SYCL for AMD device, although other combinations are also supported and known. If you want to use Apple GPUs, yeah, you still have to stick to OpenCL. It's the only backend there. And as an example, so if you have Intel GPUs, you will need to install one API-based toolkit. We recommend the currently most recent 2023.1 version that is supported on Windows and Linux. And after installing, check that your GPU is actually detected using SYCL LS, because some of the Intel GPUs might require new kernel versions or new drivers for Windows. So make sure that your GPU is actually detected, and then just build GROMACS with these parameters, with Intel compilers and GMX GPU SYCL. And you can use for multi-GPU support Intel MPI, enable it in build time, and set the quite long line, but hopefully with new versions that will shorten a bit as both we and Intel mature the features and make them less experimental. Apparently, you will need to set all these environment variables. And you can use Hefty for PME decomposition. Again, it needs a special variable to be enabled at the runtime. For AMD GPUs, the process is a bit more complicated, but it's essentially the same. You need to install first the AMD software stack, AMD ROC-M, currently supported only for Linux, although they are promising some Windows support in the next versions. Then you need to install SYCL. Unfortunately, it's not available as a binary distribution. You need to compile it yourself, but it's usually not overly complicated. Just make sure that you actually build it with ROC-M support, and later that both the ROC-M runtime and SYCL itself can detect your GPU, so all the underlying software stack works. And then you need to build GROMACS with AMD compilers, enable SYCL, and you need to explicitly specify your version of your GPU. You can see in SYCL info or ROC-M SMI output. Sorry, there's some lighting problem. And again, you can use GMX MPI for MPI support and Hefty for PME decomposition. When you use PME decomposition on AMD GPUs, you need to also add this flag to switch to ROC-FFT, because by default we use a different FFT library, VKFFT, for the FFT part of the PME computation. And also since SYCL runtime uses additional worker threads, please, again, Szilárd already mentioned, pay extra attention to your to the ping requirements if you're running on multi-GPU, multi-socket machines, and reserve a core so that worker threads have space to run. So that's it for a quick overview of SYCL, and let's push back to Berk.
Yes, so that was a lot of new performance improvements, especially with GPUs and parallelization. So now back to features, but future features. So we're thinking about future developments, or always thinking about that. And for the next release, of course, the next release cycle is already underway. But not only for the next cycle, but also further on, we need to plan what features we want to prioritize. And GROMACS development, well, it has always been user-driven, but it's even more at the focus, especially with BioExcel. So to collect input from the users and what their needs are, we're going to bring out a questionnaire quite soon. So keep your eyes open for that. That's probably going to be announced on the forum or in the announcements there. And one part there is what you as a user would like to see. And of course, users might want everything, or at least the things you're interested in. But of course, we have limited resources to implement things, so we need to make prioritization. So for that, it's good to know what the users prioritize here. So here's a list of things we could work on potentially, or maybe some things we are already working on, but we could put on higher priority. So maybe a few things will get added and things will get explained better, but here you get some idea about the things we're considering. So for instance, there's force fields with new interaction terms, so new interaction functions. There's the user-provided tabulated interactions that we have had for a long time, but that have been removed since, 2020. So there's a request getting this back. Then the GROMACS Python API, we're thinking of many extensions in different ways, but of course, we should extend it in ways that are of interest for the user. There needs to be a bit more specification here. Machine learning potentials are a very hot topic now, so that we need to consider. But of course, there are also many different options, so we need to see how to use our resources wisely. Markov state modeling has been popular and is something we are working on. So you need to see what things there we should have in GROMACS versus what things can be done with other tools. New enhanced sampling techniques, probably always of interest, and scalable constant pH molecular dynamics, of which we have a prototype running, but which still requires quite some effort to turn into production code. So that's the current list of things we have here that will end up in a questionnaire. Maybe we'll add some. You can also give feedback on this if you're enthusiastic about something, you can already ask in the Q&A now. Give some feedback here. Okay, then before finishing off, it's good to thank all the people that have been involved in this release. So we have a very long list of contributors to GROMACS, but that is the historical one since the beginning, more than two decades ago. So now we actually have two contributor lists. We also have one of people that contributed recently to this release, or things that led up to this release. So this is our list, of which some people did a lot of work, especially people in the call here and a few others, and many other people contributed with small but can still be important things, from bug fixes up to features, up to documentation improvements and tutorials and such. So it's good to acknowledge everyone that has done work here. So anyway, if any of you is interested in helping out, you will also end up on the contributor list if you provide a non-insignificant contribution. Okay, with that we've come to the end of this presentation, and now it's time for questions.
Thank you very much, all of you. So to ask question, please use the Q&A panel that is just on the bottom of your Zoom. screen. And so we had a question actually before the first part. And this question comes from Marian that is asking, is recommended tau t equal 1 picosecond and tau p equal 5 picosecond also when we use coarse-grained modeling? Or is it just for all atoms?
Yes, so I answered in the Q&A already that I suppose it works for many coarse-grained models if they're quite close to atomistic, like Martini or so. It's probably okay, but I'm not aware of the recommendations of Martini, for instance, itself. So unless it's very coarse-grained, I think it should probably work. But you can make these times a bit longer, but not that much longer. I think it is relatively uncritical nowadays with these first-order coupling algorithms. So tau p could need to be longer for things like membranes or so, which might have very slow modes. So, but even then, with first-order coupling, it usually works out. So it's far less sensitive than parallel Raman pressure coupling.
Okay, thank you. And then we have someone that decided to vote. Alexander, it was you show a list of possible future feature, and then you vote for ML potential. Maybe you can show again the slide, Berk.
Yes, should I go back to full screen, or I don't know actually how it appears here. Let's go back to full screen.
We still see your presentation.
Yeah.
Is voting for ML potential. What?
Yeah. So this term is too generic. I think when we before final, in the final questionnaire we should have a bit more detailed question, because machine learning potential is a very broad thing. So we're just discussing today in our group that there's a new paper out which seems to be promising, but then it's 1,000 times slower than GROMACS or so, and then you wonder, yes, I mean that's really problematic, and you don't even have long range electrostatics, so that's not very workable. Huh? So you would like to have machine learning potential, but much faster. So there's still some work needed there. Maybe there are things ongoing because there's lots happening in the field. So we're certainly looking into this, but we need to see at what level. But I think therefore we need a bit more specific questions so we can actually see in which direction we need to go here for machine learning potentials. Something is certainly going to happen, but we need to specify it a bit more.
Yeah, thank you. So in the meantime, I will ask you, we still have a couple of minutes. So if you have a question, please type it in the Q&A so we can, and it could be a question for Berk, for Szilárd, for Andrey. So please do it. In the meantime, we got also another vote that is for constant pH.
Yes, I agree.
And what, you agree? Yeah,
yes.
How it is the state of the constant pH?
But I have many things to do, so yeah. I can't promise anything, but I also very much like to have this in the 2024 release.
And I think following your presentation, I feel that you have also some question for the user. You ask more testing. That is true.
Well, that would be a very good idea, but then you need to formalize it. So then we need a way of systematically, because you can ask users to test, but that's very difficult to understand what actually has been done. Huh? So we need if we would have a more formal procedure for that, it could be quite useful. But then we need to have a clear specifications and clear test set. So and a clear specification of what the user has run under what circumstances and set up. So that could actually be quite useful. We're getting more stuff in here.
Yeah, we are getting more questions.
Machine learning for collective coordinates. But that's also, there's many ways to view about it. Does that mean to find collective coordinates, or to sample collective coordinates, or to define or improve? So there are many things one could think of here. There's some activities with GROMACS.
Yeah, maybe Alexander, you could specify exactly what you know, what you think. What is your opinion? In the meantime, we can go further. So we have another question. Will there be new development in GMX API in the new release? I guess the new release means
the plan, yes. So in 2024 release, yes. So we have promised to do a lot there. And I think this is a very important direction for the field, is that you can have both more scriptable and more flexible simulations. But our current issue is that we don't really have API experts in the team, so we're desperately looking for people to hire. So there seem to be a few people. There will likely a few people will be joining soon, so we have more workforce there. So hopefully we can do something before the next release. I think in the 2025 release we'll surely have much more. But for there also there's many directions, so we want to ask. But this is certainly the plan. But I don't dare to promise anything because of our current shortage of resources.
Yeah, and then we have another question on if you want back, you can just read, but you need to read the question because not everybody.
Right, not everybody might see it. So there's a last question.
So you can read it. You're welcome. I can read
which
it,
relates to the previous one is on GROMACS 2023 seems to be adopting running simulations through Python. Do you recommend using Python in the future? Well, currently we can't do enough through Python. So you can run a simulation, but it just calls the command line effectively. So there's not so much gain unless you are using a Python environment already and you want to integrate into that. But what we want to do is call GROMACS functions natively through Python or call directly C++ through a thin Python layer. But that's not there yet. So that's something, part of that we would like to have in the 2024 release, but as I said, I can't promise anything. But then also you would like to be able to set up your simulations. I mean, that's where the real gain is. I think if you can write a small Python program that prepares everything at a high level, and then you have a whole specification of your run. Ideally, you would also want to be able to modify things if you want to do more advanced stuff. But yeah, that's the kind of things we're thinking about.
Okay, so there are no more live questions. In the meantime, maybe people may become a last question. But Berk, could you give me the presenter mode so I can just make a couple of announcements? Thank you. So, okay, this was how to ask question. But so I want just to announce the next BioExcel webinar. So there will be roughly in 1 month. And will be mainly on BioBB building blocks and also BioBB building blocks API. So if you're interested, you can just look on the BioExcel webpage and register for the next webinar. The next webinar will be given by Adam Hospital from Barcelona. And then we have a last one that is BioExcel is starting again the summer school. So we had always run a summer school on the molecular simulation. And usually, traditionally, was the school in June. But this year, for more practical reason, because the project started a little later than what we were thinking. And we will have it in September. This is from the 10th to the 15th September. And it will be always in Sardinia. And the deadline for enroll is the 13th May. So please go to the BioExcel webpage if you're interested to enroll and enroll now. And that is everything from my side. So if there are no other questions, we have some thanks from some of the attendees. And if we don't have any other question, I want to thank both Andrey, Szilárd, and Berk for your presentation, all attendees to be present on the webinar, and Otto Marina for the supporting that this webinar will take place. And now I close the webinar. Thank you very much.